so there's a short answer component to the exam. So short answer and some practice problems. So we'll go over the short answer right now. So let's just go over this multiple choice short answer portion of this exam. Once again, it's Friday, just as a reminder, it's Friday. And then your quiz is also due, but I drop one quiz. So if you've taken all 3 quizzes and you're happy with the score, you do not have to turn this in. And then what else do I have to say? Might as well talk about some housekeeping. There's no lab, so if you have your lab report, you can turn it in today at 2. Just shove it underneath my door. I'll make sure I'll get the points in. And your lab notebook. If you have your lab notebook, I'll turn it in, and if it all looks good, I'll give you the 100 points. This should boost up your grade also a little bit. Okay. So lab notebook and lab report from last week. Okay, turn that into me today. Yeah. Okay, any questions on this? Okay. All right, let's just go over this exam here. So there's some question here on entropy. So let's remember what entropy means. Entropy means disorder. All right. So the most disordered state of matter is a gas. Okay. And then a liquid. And then a solid. So gas, liquid, and solid. Okay. Well, if you raise the temperature, the entropy goes up. Okay. This also increases disorder because the molecules are moving around faster. We tend to consider more mass, more stuff as entropy, because more mass, we tend to think in thermodynamics that there could be potential more motion. So anything that involves more motion, more mass, these two phenomena, increasing temperature, all of these things increase entropy. Okay, increase entropy. We're talking about entropy here now, okay, which is S. Sometimes it can be change of entropy. We're not talking about enthalpy, which is delta H, and we're not talking about delta G, which is Gibbs free energy. So coming back to this question here, a gas that goes into a solid, a gas to a solid, okay, has an entropy, what do you guys think, positive or negative? Here we have to be careful about our signage. Okay, so what will this be, positive or negative? More disorder is more positive or more negative? Okay, more disorder is more positive. Okay, more disorder is more positive. Right, so a gas has a lot of disorder. It moves around, it has more motion. A solid is very ordered. It's very ordered. It consists of unit cells. It has a density. Gases also have density, but a density of a solid is more, organized. So a gas going to a solid, I would predict that change would have an entropy that is negative, right? So you want to remember more temperature, hiking up the temperature, more mass, anything that involves more motion, that will increase entropy. So, yeah, okay. So crystal would have a negative, would be a negative entropy, okay, or solute and solvent, positive entropy, right? So more stuff, more entropy. Right. So there's about like a short answer, like positive entropy, negative entropy, so on and so forth. These are the things you want to look out for. All right, let's move on here to the second short answer part. Oxidation occurs where? In a galvanic cell. So a galvanic cell is a fancy way of saying battery. Okay, the galvanic cell has a salt bridge. And it's an anode couple, salt bridge, cathode couple, right? So we want to remember this. Anode couple, galvanic cell notation, and anode couple. Okay, these two lines represent a salt bridge and then a cathode couple. All right. So where does oxidation occur in a cell? So there's two parts of a galvanic cell. One of them is called the cathode, and one of them is called the anode. Okay. So oxidation occurs in the anode. Okay, so how do we know this? Okay. How do we know oxidation occurs at the anode? This is how I know it. I memorized something. It's called red cat eats an ox. Okay, have you heard of this? Red cat eats an ox. So so I just memorized this. Red cat means reduction occurs at the cathode, and then anode oxidation. Anode oxidation. So oxidation occurs in the anode. So then what occurs at the cathode? If we want to continue this, because I could switch it around on the exam. What occurs at the cathode? Reduction. And in a reduction, what happens? Are you gaining electrons or losing electrons? Okay, so the electrons would be on the reactant side. Okay? Okay, that's what this thing is, which you can bring to the exam. Okay, and I'll have copies available here. Okay, all of these are reductions. This is gaining 2 electrons. This is gaining 2 electrons. This is gaining an electron. Okay, so on and so forth. And then if reduction happens at the cathode where you're gaining electrons, okay, just by default what happens at the anode? Oxidation, and oxidation means lose electrons. Okay, so if I were to flip it. If I were to flip this, this would lose 2 electrons. If I were to flip this, this would lose 2 electrons. If I were to flip this for CO cobalt, this would lose 1 electron. As I flip this, I will change the sign. Okay, and it becomes the anode. All these numbers stay the same. The only thing that changes is the what? The positive, negative. Okay, those are the only thing that changes. These numbers will never alter. They are invariant. All right, so if you understand that, that's a short answer question for the exam. All right, for the half reaction, okay, we have F2 plus 2E minus goes to 2F minus. This is reduction. We're gaining 2 electrons here. All right, so this is the reduction. And it's actually standard state, so if I make it here, that's standard state. So they multiply this by what number? It looks to me, if I'm comparing this and this, they're multiplying by 3. So what will the voltage be? Okay, remember, those numbers never change. They'll never change. The only thing that changes is the sign. So this will be positive 2.87 volts. Okay, numbers never change. The only thing that changes, as Susanna mentioned, is positive, negative. All right, for the reaction to be spontaneous E cell, we have to combine the anode and the cathode. Okay, one side loses electrons, the other side gains electrons. What we want to do is cancel out the electrons, no free electrons. And for this to be spontaneous, the voltage should be positive. Okay, so we always buy positive voltage from our store. And the same thing for our electrochemical cell to be spontaneous. That means favor the products and move forward. The voltage must be positive. Okay, so let's extend this forward a little bit more. So if you have a positive voltage, okay, you have a battery. It also means if this were in equilibrium, it would favor the products. So that's a K greater than 1. Remember, this is products over reactants, and we never add solids and we never add liquids to this equilibrium constant. And then this delta G, okay, this is called the Gibbs free energy. This will be negative. Negative. Okay, all these things mean products are favored. All these things means products are favored. So what would favor reactants? Okay, the opposite. Negative voltage, we call that a dead battery, don't work. So it's not, reaction is not going to produce any voltage or any potential. The K is small, the equilibrium constant will be small because it's less than 1, and that favors reactants over the products. And then your delta G is positive. Okay, delta G, that's negative. What type of reaction we call that? Any biochemists here? Okay, we call that an exergonic reaction. Exergonic. Okay, exergonic, which means it releases free energy. Okay, it releases free energy. All right, so question like this on the exam, I could flip things around. I can say non-spontaneous, it's going to be negative, the voltage. All right, so just make sure you have those concepts in your mind clear. We'll move on here. Okay, look at this. Okay, deja vu. If K is positive, the E cell is positive, then what will the reaction, where will it favor? We have a positive K, and we have a positive voltage. Okay, so positive voltage, positive K, all of those mean that the reaction is to the product side. All right, a reducing agent. Okay, what does a reducing agent do? Okay, so this is the one where you have to think of the opposites here. So let's think of the redox couple between me and Susanna. Okay, I'm going to give an electron. Okay, I'm going to give an electron. So if I give an electron, I become negative charged, and I become positive charge. I'm so sorry. Okay, I become positive charge, and then there's my free electron. Okay, this is an electron exchange. I'm giving one electron. This is a one electron transfer reaction. So who's going to take that electron? So that's what this is. Okay, who's better? Is it going to be Susanna, Royce, Samantha, Dylan? Okay, who's better? That's what all of this table is all about. So this is a one electron transfer reaction, and Susanna is going to take that electron. Okay, when she does, she becomes Susanna minus. Okay. And we have a battery here. Okay, in this case, I am the anode, and Susanna is the cathode. She gains one electron. I lose one electron. Okay, this and this cancel, so my net is going to be this. You just replace VJ with Susanna with chemicals. You replace them with all of this stuff, and then you get a battery, anode and cathode. This is also called E cell. Okay, if it's standard state. Standard state. All right, so I get oxidized because I lose an electron. So I am a reducing agent. I am the agent that causes her reduction. Okay? I am the reducing agent. What will Susanna be? She will be the oxidizing agent. Why? Because she's the agent that caused my oxidation. Okay, so the definitions are a little backwards. A reducing agent gets a reducing agent is a substance that gets a reducing agent. It's the agent that gets oxidized. Okay, it's the agent that causes your oxidation. So this is the answer. So in this example, I am the reducing agent. Me, I'm the reducing agent because I'm the agent that causes her, Susanna's, reduction. So it can get kind of tricky, especially if you're kind of a dyslexic person, but that's the answer. You're not reducing agent gets oxidized. All right. And an oxidizing agent gets what? Reduced. Okay, so she's the oxidizing agent. Let's write that down. Susanna's the oxidizing agent. All right, so beryllium will cause the reduction of Al plus 3 to Al. Okay, is this true or false? Let's look at this here. Beryllium, where's beryllium? Okay, I'll highlight it here. Will cause the reduction of Al plus 3 to Al. So beryllium, anything above it, beryllium. Okay, anything above it stays reduced. Anything below it gets oxidized. So it's causing the reduction of Al plus 3 to Al. Reduction of Al plus 3 to Al. Where? Causes the reduction of Al plus 3 to Al. I think this is true, right? Because beryllium is up here, aluminum is up, so it stays reduced. If aluminum was below, then it would get flipped. So to me, this is true. Do you guys know how to read this? Okay. So here, beryllium, anything above beryllium stays the same, stays reduced. Anything below beryllium gets oxidized. These are the only two ways you can get a positive voltage. Right? So I'm going to put true here. Okay, true is the answer. Sodium ion will cause the oxidation of Br minus to Br2. Okay, sodium ion. Okay, let me get a fresh sheet of paper. Sodium ion will cause the oxidation of Br minus to Br2. Where's sodium ion? Okay, there's sodium ion. Will cause the oxidation of Br minus to Br2. Do you see Br anywhere here below? This is false. Okay, this is false. What can it oxidize? It can only oxidize calcium. It can oxidize strontium. It can oxidize barium. It can oxidize K, potassium. It can oxidize lithium, Li. It cannot do anything with Br. Zinc will cause the reduction of cadmium plus 2 to cadmium. Zinc. Let's look at zinc. Where is zinc? Zinc. What is this saying? Will cause the reduction of cadmium plus 2 to cadmium. Cadmium plus 2 to cadmium. I think this is correct. True. Because it will cause the reduction of cadmium plus, yeah, this is true. It can oxidize H2Mn, yeah, okay. This is true. Lithium is most likely to get reduced in the standard reduction potential table. Lithium is most likely to get reduced. What do you guys think? True or false? Negative 3.05 volts. So it's most likely to get most likely to get? What is most likely to get reduced here? Okay. Probably something like F2, which is positive 2.87 volts. Okay. So what is lithium most likely to? What's most likely to happen to lithium? It'll get oxidized, because if you oxidize it, it will be positive 3.05 volts. Right. So do you guys agree this would be false? Okay. Why is it false? What is it? Most likely to get reduced now. Most likely to get oxidized. Most likely to get oxidized, okay? Because if you oxidize it, you get positive 3.05 volts. So the answer here is false. Okay. The true statement is that lithium is most likely to get oxidized. Wait, hold on. Lithium is most likely to get reduced. Lithium is most likely to get reduced. Yeah, Li plus is most likely to get oxidized. This is correct. Okay. Because if Li plus gets oxidized, you'll have positive 3.05 volts. All right. So does everyone see why this is false? Lithium is most likely, lithium plus, lithium ion, Li plus is most likely to get oxidized. Moving on, which is the stronger oxidizing agent, Fe plus 3 or copper plus 2? Stronger oxidizing agent. Okay, so what do we look for voltages? Okay, we're looking for things that are positive. Okay, the more positive the voltage, the more likely it's going to go forward. So which is more likely to get, so what does an oxidizing agent do? It gets reduced. Okay, so which is more likely to get reduced? The one that gives you 0.77 volts or 0.15 volts? 0.77. Okay, more positive voltage, the more likely it's going to get reduced. Okay. So here, positive voltage just basically means it's moving forward. Okay. So Fe plus 3 is the answer. So if you're more positive here, you're more likely to get reduced. Okay, more positive here, you're more likely to get reduced. Okay, you flip it. Okay, you more likely, it becomes positive, you're more likely to get oxidized. All these negatives like to get oxidized. All these positives likes to stay the same and remain reduced. All right, are there any questions or comments on this? So an oxidizing agent gets reduced. Which is more likely to get reduced here? All of these are reductions. But which is more likely to get more reduced? The one that's more positive. Okay, the one that's more positive is more likely to get reduced. Okay, the one that's more negative, remember, if you flip it, it becomes positive. You can only change the sign. These negatives are more likely to get what? Oxidized. All right, some short answer there on the exam. Just make sure you're comfortable reading this thing. Okay, make sure you're comfortable reading this and then knowing some of the basics, anode, cathode, and all of that stuff. All right, so now we'll do some computation problems here for this exam. All right, so where are we at here? Write the galvanic cell notation for the following reaction. Calculate the value of E cell. Determine if the reaction is spontaneous or non-spontaneous. So for spontaneity, we're looking for a positive voltage. And this is already given to us here. This is what galvanic cell notation is. So we just need to convert this to that and then calculate a cell. So let's go ahead and do that here. All right, so here we have Cr solid going to Cr plus 3. That is Cr solid going to Cr plus 3. All right, how many electrons and where should they go to balance this out? Okay, it should be 3, right? Everyone see this? 3 electrons, and where though? Reactant side or product side? Okay, we should see this on the product side, right? Okay. Who said reactant? It's product, okay? 3 electrons go on the product side. See? Plus 3 minus 3 is equal to 0. And then reactant side is 0. All right, where is chromium here? All right, so chromium plus 3E minus goes to Cr solid. What should we do with this voltage? Okay, write it as minus 0.74 volts. Yes, we need to flip it, okay, because this loses 3 electrons. We will make this positive 0.74 volts, okay? This is the anode. Alright, so that's in the blue ink. In the black ink, let's do nickel plus 2 goes to nickel solid. Okay, so we have nickel plus 2 goes to nickel solid. How many electrons and where should this go? It should be 2 electrons on the reactant side. This balances out the charge. And is this oxidation or reduction? This is reduction, and I see nickel staring right at me. And this is negative 0.25 volts. Okay, negative 0.25 volts. This is reduction. Okay, E cathode. All right, let's add these together. We cannot have free electrons floating around, so I'm going to multiply the top one by what number? And the bottom one by what number? 3. So how many electrons are being transferred? This is a how many electrons? 6. This is a 6 electron transfer reaction. This is a 6 electron transfer reaction. All right, so let's rewrite this now. So we have 2Cr solid goes to 2Cr plus 3 aqueous plus 6E minus. And then we have here 3 nickel plus 2 plus 6E minus goes to 3 Ni solid. And so I multiply the top one by 2. This stays at 0.74 volts. I multiply the bottom half reaction, which is reduction, by 3. This stays at negative 0.25 volts. This is the most important thing I want you guys to know. And then our net reaction is just going to be this. Okay, this is just going to be this. Okay, we're going to call this E cell, and 0.74 minus 0.25 is 0.49 positive. Is that right? I believe that's positive 0.49 volts. So automatically we answer one part of this question is that it is spontaneous. Right? Okay. then let's answer this question here. The galvanic cell notation: anode couple plus cathode couple. Anode couple, salt bridge, cathode couple. So how will we write that? The anode couple here is Cr solid. You're going to draw one straight line down. Goes to Cr plus 3. Okay, that's the anode couple. Okay, how do we symbolize a salt bridge? Two lines, followed by the cathode couple, which is Ni plus 2. Okay, we're going to draw one straight line down, Ni solid. All right, so can we do this on the exam that's coming up this Friday? All right, let's do one more like this here, just to give us some extra practice. And let that, come on. All right, I'm going to avoid the numbers here, okay, just to make it easy, because you know what I'm doing? I'm taking this, I'm breaking it down into anode and cathode, and then building it back up. When I build it back up, I'll regenerate those numbers. Okay, so the way I would recommend you guys do it is don't worry about the coefficients. Okay, let's just focus on, and besides, the 2's and 2's cancel, and the 3's cancel. You know what? I should have not even put the 2's and 3's. They cancel. But anyways, that's okay. Al solid goes to Al plus 3. Okay, how many electrons and where should it go? Okay, we have 3 electrons here. This is losing 3 electrons. And let's see, where is this here? Can you guys find it? Who can find this first? Negative 1.66, but what do we need to do? Let's look at our thing here. This is losing 3 electrons, right? So we're going to flip it, and that's going to be, because I have Al going to Al plus 3, so it's losing 3 electrons. So this is going to be positive 1.66 volts. This is the anode. And then beryllium. Okay, beryllium plus 2 to beryllium solid. How many electrons and where? 2 in the reactant side. And where does that go? I see it right here. This will be negative 1.85 volts. Very good. This is the cathode. So what do we need to do here? We're going to multiply the top by 2, the bottom by 3. Just like in the previous problem, this is a 6 electron transfer reaction. Okay, let's write it all out and regenerate this. We will regenerate this. Okay, this is a 6 electron transfer reaction. Let's make that point clear. All right, now we have E cell here. 1.66 minus 1.85. What is that on our calculator? Should be negative, right? Negative 0.19. I'm getting negative 0.19 volts. This is a non-spontaneous dead battery. Okay, so this reaction, let's write the net reaction here. We have 2 Al solid plus 3 Be plus 2 aqueous goes to 3Be solid plus 2Al plus 3 aqueous. Okay, that's the same thing that we got all the way up above, but now we have E cell here at standard state, which is negative 0.19 volts, and that's non-spontaneous. And let's do the anode couple, cathode couple, and then we're done with this problem. Okay. What's the anode couple? Al solid, we're going to draw one line down, goes to Al plus 3 aqueous. Okay, what is salt bridge? Okay, two straight lines. Cathode couple. Okay, the cathode couple is Be plus 2 aqueous. We draw one straight line down, Be solid. Okay, so this and this are one and the same. All right, we have 10 more minutes. Any questions or comments here? All right, so this is kind of like what you'll see on the exam on Friday. All right, let's turn the page to page 4 here on our exam. All right, this is what I was talking about before, entropy, okay? Determining which has more disorder. So 1 mole of O2 or 1 mole of HNO3, which has more disorder? I'm going to go with the gas, okay? Even though this has more mass, the gas is definitely more disordered than something that's aqueous, right? Higher entropy. 3 moles or 2 moles? Okay, more stuff, more collisions. Yeah, 3 moles. 1 mole of sodium chloride solid or 1 mole of sodium chloride aqueous? Aqueous, because remember, water is in there. Sodium chloride and water means more collisions, more disorder. Okay, solid is a very structured material. Milk at 25 degrees or milk at 37 degrees? Okay, at 37, the milk molecules, proteins, whatever's in milk, can have more collisions and more motion. More motion at a higher temperature means more disorder, which means higher entropy. Calcium phosphate or sodium chloride? Whichever has the higher molecular weight. Okay, I'm going to guess it's this. Okay, but you would calculate the molecular weight. All right, so that is entropy. All right, so let's go on to this. Let's see if we can finish this problem here. This is E cell. Okay, this is not E cell standard state, but E cell non-standard state. So for E cell non-standard state, we will use something called the Nernst equation, which is the lecture I wanted you to watch on Friday. So if you did do that, thank you. And this should be somewhat of a review, and you'll see this type of problem on Friday. All right, so first of all, we have the anode couple. Okay, and then we have the cathode couple. And how do you know this is not standard state? How do we know this is non-standard state? The concentrations, okay? If this were standard state, it would be 1 molar. Well, this is not 1 molar. We have values for 1 molar, but we don't have values for any other concentration, any other pressure other than 1 atmosphere, and any other temperature other than 25 degrees. So those are standard state conditions. So we want E cell under these strange concentrations, or not strange, but under these non-standard concentrations. So we're going to use this equation. I'll give this to you on the exam, so you do not memorize it. This is called the Nernst equation. So first thing we'll do is calculate E cell. So this is the anode couple. So we have Mg, I'll do this in pink here. Let's first do the anode couple. Okay, how will I balance this? Okay, I'm going to balance this with 2 electrons on the product side, making it lose 2 electrons. This is anode, okay, and oxidation. Okay, where is magnesium here on our reduction potential table? It's here, but remember, all of these are reductions. So what do we have to do? We will flip magnesium sign to positive 2.37 volts. All right, that's the anode couple. Now we do the cathode couple. We have Sn plus 2 going to Sn solid. Okay, how many electrons and where? 2 on the reactant side. This is reduction. And reduction, as we know, goes in the cathode. And how many, what's the voltage associated with this? Sn, yes, point. Is this it, right? It's Sn. Yeah. So are you guys getting negative 0.14? Sn plus 2E minus goes to Sn solid. Sn plus 2 to Sn goes to Sn. Yep, I'm getting negative 0.14. Okay, so how many electrons are being transferred here? Okay, yes, this is a 2 electron transfer reaction. Okay, so in this case, N is equal to 2. And then our net here is going to be Sn plus 2 aqueous. Okay, plus magnesium solid. Plus Sn solid. Alright, so this gives us E cell here. 2.37 minus 0.14. Are you guys getting 2.23 volts? Okay, so that's going to be E cell. Okay, Q. What is Q? Okay, Q is we use Q to compare to K. And Q is products over reactants. No solids, no liquids. Okay, if Q is equal to K, we're at equilibrium. So the concentration of Mg plus 2 given to us here is 0.24 molar. The concentration of Sn plus 2 given to us here is 2.4 molar. Q and K don't have units. What is this, 110? 0.1? Is this 0.1? Yes, I got it, 0.1. Okay, good. So now we can solve this. All right, so let's do that, and then we'll finish this off on Wednesday. All right, so E is equal to E cell, 2.23 volts minus 0.0257 volts divided by 2 natural log of Q, which is 0.1. Okay, and this should give us our answer. Okay, do we know how to do this on our calculator? Okay. Natural log of 0.1. Okay, times a minus. I want everyone to realize it's times a minus. What's the sign here in front of the 0.0257? Minus. So it's going to be times a negative 0.0257 divided by what number? 2 plus 2.23 plus 2.23, and we're getting about 2.26 volts. Okay, this is the answer. E cell under these concentrations. Okay, so notice it's 2.23 volts. If you up the concentrations a little bit, you can get it to 2.26 volts. Okay, if you go the magnesium to 0.24 and the SN, I think SN is 10, SN to 2.4. Okay, you get a slight uptick in your voltage. All right, so that is the answer there. Okay. We have one more problem, and we will do that on Wednesday. So come with your questions on Wednesday, and then turn in your lab notebook today if you're in my Monday lab, and turn in your lab report today if you are in my Monday lab, and I'll get those points in.
Just slide it under your door.
Yeah, I'll be here at 2, so you can hand it in to me. But if I happen to not be in, you can slide it underneath. Lab notebook may be a little more difficult. You'll have to arrange to come give it to me. But I should be in at 2 o'clock. We're not meeting in the lab. You just come in my office. Don't. Okay. Oh, you're all done.
Your lab aids, because I rewrote my stuff, so I just need them to reinitial.